Last, I'd like to welcome Madhav Chitturi from the University of Wisconsin.
Hello, thank you for being here, and thank you for this opportunity to present to all of you, and thanks to CCAT for funding this research effort. So I would like to acknowledge David Noyes is the PI for this project. David Noyes is the PI for this project, and Sky and Sue, their co-PIs, and Cesar was a student who worked along with me on this project. So I want to give a background what got us going onto this topic here. So a few years ago, we started looking at AV crashes. Once Google released their data, and also the standing general order data from NHTSA was going to come out. So we said, let's visit what has been done in terms of evaluation of the AV crashes. So this is not our paper. I have the citation at the bottom here of the slide. This is one of the earliest evaluations of the Caltrans crash reports, AV crash reports. So there are only 12 crashes in the time period, September to November 2015. So I copy-pasted these two sentences. Essentially what they're saying is, out of the 12 crashes, there's only one crash where the AV was at fault, and AV was, the other vehicle did not behave the way AV was expecting it to behave, the human-driven vehicle. Right? That was interesting. And if you read the first part of it, it says in the other 11 crashes, in most cases, the drivers were surprised by the way they interacted with them. So this was kind of the initial seed for this thought about expectancies are at play. And again, we do this all the time, maybe unconsciously as we drive, right? But we are always calculating, if you are seeing a pedestrian crossing in a crosswalk, you're making a turning, you're seeing, okay, by the time I get to the crossing, is there going to be a conflict or not, right? We do this all the time. So we said, okay, let's do an evaluation. So this was in 2020, we had a paper published on this one. So at that time, we got about a few years of crash data from California DMV, 168 crashes. So we found about 7 crash patterns. This was not the primary focus. We just wanted to see what are the patterns in AV crashes, right? That was the topic of this paper. So I want to zoom in, I won't go through all those 7 patterns there. I want to zoom into the second pattern there. So we call it hesitation. What we mean by that is the blue vehicle is the AV, the black one is the human-driven vehicle behind the AV. So AV is waiting at an intersection to make a left turn, right? The signal turns green, it's a permissive left turn, so you have to yield to the opposing traffic before you make your turn. So the AV starts going, so that's the second column over there, the AV starts going. You don't see the tail lights, the brake lights lighting up anymore. And for some reason, the AV brakes again, and we have a few crashes. I believe about 8% or so of the crashes in this case, out of those 168, was the AV was rear-ended by the vehicle behind. So we call it hesitation, right? So again, so this was the basis we wanted to examine, if other patterns show up where these expectancy violations are at play. So that was the basis for this project, and I want to show you this video here, which kind of illustrates that. But before I play it, I want to say in this instance, the AV did the right thing. Apparently, there was a vehicle from the left, which we don't see in this video, which ran the red light or was going to run the red light, so the AV decided to brake. So in this instance, Waymo did the right thing, but this is just to illustrate, what is the hesitation scenario I talked about. So I'll play that once again if you want. Okay, there it goes. So the light turns green, Waymo starts moving, decides to brake again. Okay, so you can see the following vehicle, that's the Arizona Republic, the media, they were following this Waymo vehicle. They caught this video. Anyway, so this is the kind of scenarios we are talking about. You don't expect it once the vehicle starts going, at least not all the time anyway, it's not usual. And when it happens, there is a chance for a collision, at least a near miss. Okay, so I'll be quick. I know we are running short of time here, but the methods I'll go quickly. So what we did was, generally in safety analysis, we are looking at manner of collision, crash type thing, right? We are not looking at the entire sequence of events. What happened prior to there being a rear-end crash or an angle crash? So what we said was we really have to look at the sequence of events, not just once the collision happens, what was the point of impact, and based on that, what is the manner of collision. So we call this a crash sequence analysis. And the first step, obviously, you collect data. Between these two, the AV data from Caltrans and then the standing general order from NHTSA, we got about 555 crashes. So essentially what we do is we read the narratives. Yes, we did this manually. This was before all the LLMs were here and before we checked the LLM, trust the LLM to do it for us. But what we do is essentially we read the narrative and we convert it into these discrete events, right? One question is, how do you define these events? CRSS, it's a NHTSA's database. It already has a dictionary of events they use for CRSS and FARS. So we modified that a little bit. Essentially, we followed their terminology. So take the narrative, turn it into a sequence of events, right? And then what we do is we had to compare sequences because we are trying to see which crashes are together, or similar type or similar cluster. What we are trying to do is, what does it cost to turn or transform one sequence into another sequence? In this case, right, we have to, for example, in the second sequence at the bottom, we had to remove that V2 change lanes and then insert these two, V1 stop, V1 yield, right? So it's called insertion or deletion. Without going into the details again, essentially you do this for all possible pairs of crashes and you come up with the dissimilarity matrix, right? That's the one on the right side at the bottom there, which says how much would it cost to turn one crash sequence into another crash sequence. And then we use this dissimilarity matrix to say, okay, now I know how far apart or how much does it cost to transform one crash to the other, and based on that, we do clustering. We use the K-Medaillards clustering to come up with the number of crash patterns clusters. And then finally, we have to come up with, okay, what does this cluster mean? For example, group 4, it is a vehicle turning right, and then there's a crash, right? So based on these 555 crashes, we got about 13 clusters. We grouped them into 12 groups. Now, we got this published last year. That paper, because we had to get it published, we focused beyond just expectancy violations. It compared AV and human-driven vehicles, right? We had similar clusters for human-driven vehicle crashes as well. But now, in this context of expectancy violations, group 4 and 5, one is right-turning vehicle and one is a left-turning vehicle at an intersection. And I guess before I get into the details here, one thing what we notice, it's probably all of you are familiar with it, intersections are really a challenge for the automated vehicles. Nearly 2/3 of these 555 crashes happened at intersections. Only 1/3 happened at segments, so to speak. So anyway, so turning movements, again, as you can see, about 76 out of those 555 are these two groups, turning crashes. So you can see in both these cases, right? The first one is, the data set includes Waymo and Cruise, so it's not just Waymo, but to illustrate, I have two examples here. Both these happen to be for Waymo, right? But there are other crashes where Cruise vehicles were also involved. So the vehicle is, right turn on red, and then it gets rear-ended, right? That's the first one. And the second one, again, it's a permissive left turn, and it sees oncoming traffic, it decides to brake, the video that I showed you earlier. So that still remains an issue here. As I said, it was only about 8% in the first analysis we did in 2021, but now it's a significantly higher percent. The second one we found was vehicles crossing. So in this case, the AV is not at fault per se. The AV, it came to a stop, and then it was its right of way, it was going ahead, and then it got, from the side. So that's the first instance you can see. In the second case, it's interesting, there's actually a traffic light, and a fire truck is involved with emergency lights on. Still, Cruise vehicle decided to go forward, and then it got hit, right? So in these two, and there again, as I said, about 36 out of those 555 crashes, other vehicles were violating the AV's expectancy, right? AV's, it's my turn, the signal is green, I got to go, or stop sign, it's my turn to go, but then other vehicles come in. So what this data suggests is, practical implication, right, from an AV safety perspective. We need to account for these expectancies now. Now, if we add in VRUs, which they talked about, right, Vineet and Carol here. So that's a whole set of other scenarios that would show up, but right now they don't show up in our clusters. And quickly, we have also looked at temporal trends. How does this vary? These 12 groups, how do they vary over time? Because obviously, we heard, right, in this other discussion, AVs are always being updated. So we would expect that, okay, they're mitigating the types of crashes or incidents that they're seeing, near misses. Hopefully, it's not an issue anymore. So this is for the turning movements, group 4 and group 5. And if you focus on those two colors, the pink and the gray at the bottom, you can see initially there are hardly any left turning crashes, and which is interesting, right? Most of them in the gray color, they're the right turning vehicles. But we also know that in the beginning, we can also read it in the narratives. Most of these permissive left turn movements, the safety drivers were taking over. The vehicle was not operating in an automated mode to make those turns. Our hunch is probably that's the reason they don't show up, the left turning crashes in the beginning. But then they do show up. Again, it's a smaller proportion, right? But they do show up. And this is for those vehicles crossing, the blue color, as you can see there. Again, it's a smaller proportion compared to the turning vehicles, but it has been there. One thing we did notice was, actually I'll talk about in the next slide. We also said, okay, does this vary between Waymo and Cruise? Because different algorithms, different sensors and everything. So interestingly, you can see, again, I have those boxes around those groups 4 and 5, which is the turning vehicles. And it's Waymo, at least in that category, larger proportion is Waymo, right? The green bar, as opposed to the yellow bar. And on the flip side, when you go to this crossing movements, number 8, almost 80% of the crashes are for Cruise and 20% are for Waymo. So when we first saw this, that group 8, right, other vehicles are violating and hitting AVs, one thought came to us was, is this just, vehicles, human-driven vehicles, some of them being not nice to the AVs, right? But then when we saw this, that it's mostly 80% of these are Cruise and only 20% or less. And I should also note, those 20% which are from Waymo are from the earlier years. Pretty much in the last 2-3 years, there's hardly any crash in that group from Waymo. So that suggests, if it's like people's antipathy towards AVs, you'd expect both Waymo and Cruise vehicles to have this type of crash, right? That's not the case. So kind of indicates maybe there's something that Cruise has to work on here. So in terms of findings, so we did, based on, again, narratives, and yes, there is some subjectivity in it. I would acknowledge that, right? But there seems to be this expectancy violations contributing to some of these crashes that we are seeing. One is AV violating the expectancy. That's the first one, which is hesitation we saw in that video as well, right? In making permissive movements, left turn or right turn. Permissive movements are a problem, looks like. And the second one is the human-driven vehicle violating the AV's expectancy. The AV has the right of way, but then you still end up in crashes. Now, I kind of alluded to this. There are other scenarios where we could have this same phenomenon, at play. For example, change interval at signalized intersections. Imagine AV is the vehicle ahead of us. We are driving behind it. The signal turns green to yellow. Based on where we are at in the dilemma zone, we have an assessment, will the lead vehicle go or decide to stop, right? And we try to base our response based on that. Now, if the AV were to be, I want to be ultra conservative, I'm going to stop, I'm not having any passengers in the vehicle, deceleration rate doesn't matter, I'm going to stop, for example. Now, that can lead to a near miss or a crash, right? And another example is turning vehicles yielding to peds at crosswalks. So, this we do all the time, right? When we are at a turning, there's a pedestrian in the crosswalk, we kind of assess by the time we get to that lane, make the turning movement, is the ped cleared our, where we are going to be our lane. But, and then the following vehicle also does the same thing, right? So if the lead vehicle were to be an AV and they decide we are going to stop, we want to be polite to the pedestrians. It's nice. But then that can create an expectancy violation for the following human-driven vehicle, right? And I'm sure all of us can come up with some more, and if you have some more ideas, I'm happy to hear and take notes. So in terms of future work, what we plan to do is, as I said, Sky Chen, he is a faculty member, he is a co-PA on this project, and as part of CCAT and his other research efforts, he has developed this distributed multi-agent architecture. You can have human-driven vehicles, AVs, and pedestrians, all of them, interacting in the same virtual environment. So hopefully with CCAT funding, we'll want to explore some of these AV, HD, VVR interactions and see how do these play out, right? Do we actually see near misses? Do we see any crashes? And that could be the future work. Thank you. Any questions?
Okay, well, let's give all of our lecturers a big hand. Thank you.
Thank you.